in the works. Thank you. No blockers.
Hello, sir. Hello.
Hold on a second, sir. Sir, you are the host now.
Yes. Thank you. Good evening, everybody.
Good evening, sir.
Yes, good evening. So we have come to the last part of the chapter, chemical kinetics. Last part of the chapter. Maybe today and one more class, one more session I might require to complete the chapter. We'll continue with the theory part of the chapter today, and the questions based on the competitive exams, we will work it next class. Now, we have theories of reaction rate. Various theories proposed for reaction rate. The first one is called as collision theory. The first theory, or in our syllabus, we have only one theory to be learned, that is called as collision theory. Now, in the atmosphere, we have oxygen and nitrogen. In the atmosphere, we have oxygen and nitrogen. Now, these oxygen and nitrogen, which is in the atmosphere, they constantly collide with each other. They collide with each other. When this oxygen and nitrogen, when they collide with each other, do they react to give any products? Do they react to give any products? I'm asking you a question. Nitrogen and oxygen is in the atmosphere. These are gases. Gases are in random motion. They collide with each other. When they collide with each other, is there any product formed? You can tell me, you can participate and tell me.
No, sir.
No products formed. Why there is no products formed? Because the energy at which these collide is not enough to bring about the reaction. But the same reaction during thunderstorms, during lightnings, thunderstorms, what happens? Nitrogen and oxygen reacts to form nitric oxide, and this nitric oxide combines with water, and it comes in the form of nitric acid, and we call that as acid rain. You would have heard of the term called as acid rain. So at higher temperature, what happens? These nitrogen and oxygen reacts to form nitric acid, and which comes to the earth in the form of acid rain. We are not talking about the concept acid rain here. Now we are talking something called as collision theory. Now, what is this collision theory? Now, collision theory clearly says that the reactant molecules have to collide with each other to form a product. To undergo a reaction, the reactant molecules or reactant atoms has to collide with each other. That is what the collision theory proposes. Now, in this, all collisions are not fruitful. The first point you should remember, all collisions are not fruitful. When I say all collisions are not fruitful, it means all collisions are not effective otherwise. Now, when I say all collisions are not fruitful or not effective, it means all collisions will not lead to the formation of the product. Like nitrogen and oxygen in the atmosphere, they are colliding, but still there is no change. There is no reaction. So they are called as non-effective collision, or they are called as not fruitful collision because product is not formed. Because they collide with minimum energy, that energy is called as normal energy. That energy is called as normal energy and represented as En. So the first energy, what we're trying to understand, is called as normal energy. Every reactant molecule will possess some amount of energy. And when that energy is called as normal energy, when the molecules collide with normal energy, it will not lead to the formation of the product. They are called as ineffective collision, or they are called as non-fruitful collision, the first point. Second point, I told you, during thunderstorms, nitrogen and oxygen will collide and it leads to the formation of the product because the energy is what? High during thunderstorms. The molecules gain more energy during thunderstorms. Therefore, when they collide, they lead to the formation of the product. Meaning, now every molecule which has normal energy, it has to gain some excess energy. The excess energy gained by the reactant molecules, to undergo effective collision. Is called as activation energy. This activation energy is represented as EA, capital E and small letter A. Now, what's the statement? First, I told you all collisions are not fruitful. All collisions are not effective because energy associated with those molecules are less. They are called as normal energy. Now, if a molecule has to undergo a fruitful collision, if a molecule has to undergo an effective collision, when they collide, if the products have to be formed, they have to gain little excess energy. That excess energy, what the molecules gain, is called as activation energy. It is otherwise called as energy of activation. The third point is this threshold energy. This threshold energy is represented by ETH. This threshold energy is the sum of normal energy and activation energy. The sum of normal energy and activation energy is called as threshold energy. So if a molecule gains energy above threshold energy, then whenever the molecules collide, it will lead to the formation of the product. And that kind of collisions will be called as effective collisions, or it is called as fruitful collision. Did you follow this? These 3 points, did you follow?
Yes, sir.
Yes. Now, theories of the reaction rate. The first theory, what we're learning is collision theory. I'm going to give you the graphical representation of this collision theory. Before the graphical representation, we will try to understand the concepts here. The basic requirement for a reaction to occur is that the reactant species must collide with each other or with one another. I clearly told you this. This is the basis for collision theory. So the reactant molecules have to collide with each other. That's the basis. Second, the number of collisions takes place per second per unit volume. Number of collisions 1 second in 1 liter volume is called as collision frequency. It's called as number of collisions that takes place per second per unit volume. The value of collision frequency is very high, 10 to the power 25 to 10 to the power 28. Just imagine 10 to the power 25, 10 to the power 28 times per second, the collisions for a binary collision. That means two molecules can collide 10 to the power 25 times to 10 to the power 28 times per second. That means collision is very, very fast, very, very high. So that, what's that collision frequency is number of collisions which takes place per second per unit volume is called as collision frequency, and it's represented by letter Z. Collision, every collision does not bring about chemical reaction. I clearly told you, because if the energy of the colliding molecules are less, if the molecules collide only with the normal energy what it possesses, it will not bring about the chemical change. It will not bring about the reaction. The collision that actually produces the products are called as effective collisions. This effective collisions is otherwise called as fruitful collision, otherwise called as fruitful collisions. The effective collisions which brings about chemical change are few in comparison to total number of collisions. So you should remember that collision, the effective collision, which brings about the change, a chemical change, are few in comparison to the total number of collisions. The collisions that do not form products are called as ineffective elastic collisions. Ineffective elastic collisions. When I say elastic collision, energy will be transferred from one molecule to the other molecule, but there won't be product formation. Those are also called as ineffective elastic collisions. That is, the molecules must collide and disperse in different directions with different velocities. So molecules must collide and disperse, move away in different directions in different velocities. We'll come to this graph in a minute time. We will learn, for a collision to be effective, the following two barriers are to be cleared. The first one is energy barrier. I told you the minimum amount of energy which the colliding molecule must possess to make the chemical reaction to occur is called as threshold energy. I clearly told you threshold energy is the sum of normal energy and activation energy. Every reactant molecule will possess some amount of energy. That's called as normal energy. With normal energy, if the molecule collides, it will not lead to the formation of the product. Therefore, it has to gain some extra energy. Minimum excess energy gained by the molecule in order to undergo effective collision is called as activation energy. So sum of activation energy and normal energy is called as threshold energy. If a reactant molecule overcomes the threshold energy, when they collide, it will lead to the formation of the product. That's called as threshold energy. Did you understand what is threshold energy? Respond.
Yes, sir.
Now, in the graph, E corresponds to minimum or threshold energy. We will talk about the graph a little later. One is the energy barrier. The reactant molecules have to overcome the energy barrier. The second one is orientation barrier. You know what is orientation? Orientation is the arrangement of atoms or group of atoms in space is called as orientation. All these molecules have structures. All these in a molecule, the atoms are spaced in the three-dimensional representation. So the proper orientation means proper representation of atoms in a molecule in three-dimensional space is called as orientation. So if the molecule have to undergo effective collision, it has to overcome something called as orientation barrier. Colliding molecules should also have proper orientation so that the old bonds may break and new bonds are formed. For example, NO2 and NO2 giving you N2O4. That is, nitrogen dioxide reacts with each other to form nitrogen tetroxide. During this reaction, the products are formed only when the colliding molecules have proper orientation at the time of collision. These are called as effective collision. Now just look at the representation. This is nitrogen and 2 oxygen, nitrogen dioxide. This is nitrogen, 2 oxygen, nitrogen dioxide. They collide. See, this oxygen atom collides with what? Nitrogen. That's what they say. When oxygen atom collides with nitrogen, what happens is the molecules separate each other. They move away from each other. So they are not oriented in space properly. Therefore, no products is formed. But if you observe the second representation, this is nitrogen dioxide, this is nitrogen dioxide. When nitrogen atoms collide with each other, a proper bond is formed between what? Nitrogens, both the nitrogen atoms. Therefore, a product N2O4 is formed. So orientation of atoms in a molecule is one more factor to overcome in order to undergo an effective collision. Not only the energy barrier, the other barrier is orientation barrier. No problem with this? Did you understand? Followed? Followed or?
Yes, sir. Followed.
Thus, the main point of collision theory is as follows. For a reaction to occur, there must be collision between the reacting species. Only a certain fraction of total molecules, a total number of collisions is effective in the forming the products. For effective collision, the molecule should possess sufficient energy as well as proper orientation. These are the three conditions for a molecule to undergo effective collision. The fraction of effective collision under ordinary condition may be vary from nearly 0 to about 1 for ordinary reaction. Thus, the rate of reaction is proportional to, okay, we will come to this concept a little later. All right, before we come to this concept, we will learn something called as the graphical representation. The graphical representation is like this. This is potential energy. Potential energy versus the reaction path. Reaction path, or it is called as reaction coordinate. Reaction coordinate, coordinate. Now, I'll ask you a question. Now, if hydrogen and iodine is allowed to react, what's the product we get? What's the product we get?
Sir, hydrogen iodide.
Hydrogen iodide. What's the definition of chemical kinetics? We learned chemical kinetics as a branch in physical chemistry, which deals with the rates of the reaction as well as mechanism of the reaction. So this reaction is not giving you the mechanism. It's only a representation. The reactants reacts to give you the product. So this reaction is not giving you the mechanism. So this mechanism can be learned from the collision theory. Now, what is that mechanism? Now, just observe. This is reactants. Hydrogen and iodine are reactants. These hydrogen and iodine, which possesses normal energy, when they collide, no products are formed. No products are formed because the collision is weak. Therefore, it's an ineffective collision. Therefore, no products formed. So in order to form product, these reactants has to gain some energy. What is that energy it has to gain? What is that energy it has to gain? What is that energy it has to gain? Tell me. This is normal energy. In order to undergo effective collision, it has to gain what energy? What energy? I wrote here, what is that energy it has to gain? Activation energy. So when the reactant molecules gain activation energy, products are not formed. An intermediate product is formed. When I say intermediate product, this intermediate product will be highly unstable. They will have excess energy. This is the intermediate product. See, H2 and I2, they form an intermediate product. This intermediate product, or this is also called as activated complex. It is also called as activated complex. Intermediate product or activated complex. This energy is called as threshold energy. This is called as threshold energy. The sum of normal energy and activation energy is called as threshold energy. So an intermediate compound is formed, or an activated complex is formed. This intermediate compound or activated complex, they have very high energy. How is energy related to stability? How is energy related to stability? Energy is inversely proportional to stability. When we say energy is inversely proportional to stability, it means greater the energy, the molecule is highly unstable. Now, this activated complex has high energy. Since they have high energy, they decompose to form the products. They decompose to form the products. The product is 2HI. The product is 2HI. Now you can see the products which are formed has lesser energy. This is the product compared to the reactants. So the difference between the energy possessed by the reactant and the product is represented as delta H. Are you following? This is called as energy profile diagram. Energy profile diagram. To explain the collision theory. Did you understand this? Now, all the reactant molecules will possess minimum amount of energy. That's called as normal energy. When they collide with normal energy, no reaction takes place. No products are formed. Collisions are ineffective. In order to undergo effective collision, these reactants has to gain some energy. That excess energy the reactant molecules have to gain is called as activation energy. So when the molecule gets activated, the molecules react with each other to form an intermediate compound or to form an activated complex. This activated complex has excess energy, higher energy. Therefore, they have minimum stability. They decompose to give product. So how do I write the reaction? So this is the reaction overall. Now the reaction as per the mechanism is H2 plus I2. They react to form an intermediate compound. This intermediate compound which is formed is unstable. They decompose to form product. This is the mechanism of the reaction. This is the mechanism of the reaction which can be understood by collision theory. Did you follow this graph and explanation? Nobody's responding. Are you there?
Yes, sir.
Please tell Dhanalakshmi. Keep
So once again, you repeat it, sir, just as a glance.
So you're not even responding, huh? You should. Otherwise, how will I know whether you're following or not? Now, the reaction is hydrogen and iodine. The reaction is between hydrogen and iodine. Now, this hydrogen and iodine, they have minimum amount of energy. When they collide, no products are formed because energy is less. That's called as normal energy. Ineffective collision, not fruitful collision. So if they have to form product, these nitrogen and hydrogen, they have to gain energy. When I say they have to gain energy, how can they gain energy? They can gain energy in the form of heat. We have to supply heat. Or it can gain energy from the sunlight. So when they gain energy, what happens? That energy, what it gains, excess, is called as activation energy. So when they gain activation energy, they overcome something called as threshold energy. When they overcome threshold energy, this hydrogen and iodine will react to form an intermediate compound called as or activated complex. This intermediate compound or activated complex, they have high energy, therefore they're highly unstable. So they're highly unstable, they will decompose to form a product. Now the product formed is what? Hydrogen iodide. Now you can see the energy associated with the product is much lesser compared to the energy associated with the reactants. Therefore, products are more stable than what? The reactants. Follow now?
Yes, sir. Yes.
Okay. Now coming back to these concepts now. The fraction of effective collision under ordinary condition may vary from 0 to about 1 for ordinary reactions. Thus, the reaction rate is proportional to, see, reaction rate. The rate of a reaction is represented as dx by dt. Why this minus sign? This minus sign indicates the decrease in concentration of the reactant. So minus, that is equal to F into Z. This Z, we know it is called as collision frequency. Collision frequency. And the fraction of the effective collision is represented by letter F. So fraction of effective collision or the small amount of effective collision is represented by letter F. So the rate of a reaction is fraction of effective collision into the collision frequency. We defined what is collision frequency. Number of collisions per unit volume per second or number of effective collision per second per unit volume. So number of collisions per second per unit volume is of the range 10 to the power 25 to 10 to the power 28. We learned, even though the number of collisions are very high, only few undergoes what? Effective collision. That small amount of molecules which undergoes effective collisions is represented by a letter F. Fraction is a small value. So fraction is a small letter F. Therefore, the rate of a reaction is represented as minus dx by dt, that is equal to F into x. F is fraction of effective collision and Z is collision frequency. Now, the physical meaning of activation energy is that it is minimum relative kinetic energy which the reactant molecule must possess for changing into products. So the physical meaning of activation energy is the minimum excess energy, minimum relative kinetic energy which a reactant molecule must possess for changing into product molecules during their collision. This means that the fraction of successful collision is equal to E is equal to minus EA by RT. So successful collision is given by a factor E is equal to minus EA by RT. EA is activation energy, R is a gas constant, T is a temperature. Likewise, it may be noted that beside the requirements of sufficient energy, the molecule must possess proper orientation. We learned this orientation also with example of N2O4, nitrogen tetroxide, to be successful. Thus, ZAB is called as collision frequency and P is called as orientation factor. This orientation factor is also called a steric factor. Steric factor means space, arrangement of atoms in space. Therefore, we can write K, rate constant K is equal to PZAB into e to the power minus EA by RT. P is called as orientation factor and ZAB is called as ZAB is called as collision frequency and E is called as exponential factor, EA is activation energy and R is gas constant, T is temperature. We can compare this equation with Arrhenius equation. We can compare this equation. Look at this equation. K is equal to P into ZAB. What is this Z? Z is collision frequency. AB are atoms or molecules which are involved in collision into e to the power minus EA by RT. This is looking similar to this equation. K is equal to A into e to the power minus EA by RT. This equation is called as Arrhenius equation. They can ask you in your 12th standard, write Arrhenius equation and explain the terms involved in it. Write Arrhenius equation and explain the terms involved in it. Arrhenius equation is given by K is equal to A into e to the power minus EA by RT. What is this K? K is called as rate constant. K is called as rate constant. A is called as collision frequency, not collision frequency. It's called as frequency factor. Frequency factor or Arrhenius frequency. Arrhenius frequency. Arrhenius factor, sorry, Arrhenius factor. You can call it as Arrhenius frequency also. It's termed as Arrhenius frequency also. And E is exponential factor. And EA is energy of activation. And R is gas constant. You know the value for gas constant. And T is the temperature. So you have to write this equation and explain the terms involved in it. So K is called as rate constant, A is called as frequency factor or Arrhenius factor, EA is energy of activation, R is the gas constant, and T is the temperature. Now this this A and EA together, this frequency factor and energy of activation together are called as Arrhenius parameter. Arrhenius is a name of a scientist. Arrhenius is a name of a scientist. So collectively, Arrhenius factor and energy of activation together, they are called as Arrhenius parameter. Followed with this? Followed? Followed or not? You tell me.
Followed, sir.
Why it's so long you take to respond? Is there any problem with the connectivity?
Sir, I'm wearing headphones, sir. It's taking time to unmute and speak, sir.
Others? All right, the last part of the topic, one derivation we have, and we'll have to solve some of the questions. Based on that, we will do the derivation. The derivation is there in your syllabus. And based on that derivation, based on the formula what we derive, there will be questions in your competitive exam. It's a lengthy problems, and they will be asking it in your competitive exams. The derivation is to calculate the energy of activation at two different temperatures. All right. So the derivation is, well, the question can be asked like this: derive an expression to calculate the energy of activation, at two different temperatures. This is the derivation what we're supposed to learn. This is the last part of the topic in chemical kinetics. All right. Derive an expression to calculate the energy of activation at two different temperatures. Now, in order to derive this equation, we should use the Arrhenius equation. Now, we know we can start the derivation like this. We know that K is equal to A into e to the power minus EA by RT. This is nothing but what equation? Arrhenius equation. K is called as rate constant. A is called as Arrhenius factor, frequency factor. E is energy of activation. R is the gas constant. And T is the temperature. Now, taking log on both the sides. Taking log. When I say log, I'm taking natural log. Natural log is represented as ln. Natural log is represented as ln. Log to the base e is called as natural log. Taking natural log on both sides, we can write natural log of k is equal to natural log of a into e to the power minus EA by RT. So taking natural log on both the sides, we can write log k, natural log of k is equal to natural log of A into e to the power minus EA by RT. So this can be written as natural log of k is equal to log AB can be written as what? Log AB can be written as log A plus log B. So likewise, you can see this A is one factor and e to the power minus EA by RT is another factor. So therefore, we can write this as natural log of A minus natural log of e to the power minus EA by RT. Now, I told you for natural log, the base is E. Now, for log also the base is E, and for this factor also the base is E. Therefore, this E will get cancelled. E will get cancelled. Now, when E gets cancelled, likewise, the log also get cancelled. Log also get cancelled. Therefore, we can write natural log of K will be equal to natural log of A minus EA by RT. There should not be a minus here. There should not be a minus here. Minus sign will get cancelled. So it will be minus EA by RT. Now, two different temperatures I spoke. The question is, derive an expression to calculate energy of activation at two different temperatures. Now, maybe we can write at low temperature, T1, we can write this equation as natural log of K1 is equal to natural log of A minus EA by RT1. We can write it as natural log of A minus RT1. We will mark this as equation number 1. The second is, maybe we can write here at high temperature. At high temperature, we can represent high temperature to be T2. At high temperature, we can write this equation as, we can write this equation as natural log of K2 is equal to natural log of A minus EA by RT2. This is equation 2. Now we can see the equation 2 is larger value because temperature is high. So equation 2 minus equation 1. So when you subtract equation 2 from equation 1, we can write natural log of K2 minus natural log of K1 will be equal to natural log of A minus EA by RT2 minus of natural log of A minus EA by RT1. So now log A minus log B can be written as what? Log A by B. So we can write this as natural log of K2 by K1. Now when you open the brackets, what happens? When you open this brackets, what happens? Natural log of A minus EA by RT2 minus natural log of A. This minus and this minus becomes plus of EA by RT1. So now just observe this. This natural log of A and this natural log of A gets cancelled. This is plus and this is minus, gets cancelled. So what we can write, natural log of K2 by K1 will be equal to, see this is a minus sign here and this is a plus sign. I can write it as EA by RT1 minus EA by RT2. Hopefully I have space, yes. Now what happens? This natural log of K2 by K1, we can write, what's the common factor here? EA by R is a common factor in both. So when you take EA by R as common, we can write 1 by T1 minus 1 by T2. Now we can write this as natural log of K2 by K1 is equal to EA by R. You can take LCM. It will be T1, T2. That will be equal to what? That will be written as what? T2 minus what? T2 minus T1. If you take the LCM. T1, T2. T1 will get cancelled here and T2 into 1 is T2 minus of T2 will get cancelled here and you will get T1. So T2 minus T1 divided by T1, T2. How do you convert natural log to the base 10? The conversion factor is 2.303. When you multiply this factor by 2.303, natural log gets converted to log to the base 10. See, this is ln, this is natural log. Here I'm writing log, log to the base 10. So it will be K2 by K1. That will be equal to EA by R, T2 minus T1 divided by T1. Or we can write this equation as log to the base 10 of K2 by K1 is equal to EA by, we can take this 2.303 to denominator here, 2.303 R into T2 minus T1 divided by T1, T2. This is the formula to calculate the energy of activation at two different temperature. Based on this, there can be a competitive question or maybe a regular 12th standard question also they can ask you based on this formula. All right, now I will revise this question one more time. And if you have any clarification, you can get it done a little later. The question is, derive an expression to calculate energy of activation at two different temperatures. This is Arrhenius equation. We know according to Arrhenius, K is equal to A into e to the power minus EA by RT. This is Arrhenius equation. We explain what is K, what is A, what is EA, what is RT, all that we explain. Taking natural log on both the sides, LN stands for natural log. When we take natural log on both the sides, we can write natural log of K is equal to natural log of A into e to the power minus EA by RT. Now, natural log of K will be equal to, this is in the form log AB. Log AB can be written as log AB can be written as log A plus log B. Sorry, I made a mistake here. Log A plus log B. Therefore, this minus and plus becomes minus sign. I made a mistake. Sorry. This is log A plus log B. So natural log of A plus of natural log of e to the power minus EA by RT. Since the base for the log is E and the base for this value is E gets cancelled as well as the log gets cancelled. So plus into minus becomes a minus sign. So we write natural log of K is equal to natural log of A minus EA by RT. This is the general equation. Now we write this equation at two different temperatures. One is at low temperature and the other one is at high temperature. Low temperature, we take K as K1 and T as T1. So natural log of K1 is equal to log of A minus EA by RT1. That is equation 1. And at high temperature, we take natural log of K2 is equal to natural log of A minus EA by RT2. We mark it as equation 2. So equation 2 minus equation 1, and it's complete mathematics. You can see, if you have any clarification, you can ask me. And then we come to the conclusion. The equation at two different temperatures to calculate energy of activation is log to the base 10 of K2 by K1, that's equal to EA by 2.303 R into T2 minus T1 divided by T1, T2. You can just go through, and if you have any clarifications, you can ask. Any clarifications, students?
No, sir.
Everybody followed with this? All right. Now, we'll have to derive. I think I taught you one more topic yesterday. Last class, not yesterday. Before that, I will teach that question also one more time. I'll erase this part. I hope that everybody understood. I'll erase this derivation, and so that we can do one more small topic and then continue with some of the questions possible. Now, we learned in the last class something called as a temperature coefficient. Was anybody there when we were learning temperature coefficient?
No, sir.
You weren't there. All right. So this temperature coefficient I will teach you, and then we'll work out some problems based on the topic. What happens to a chemical reaction when we increase the temperature? What happens to a chemical reaction when temperature is increased?
So reaction becomes faster, sir.
The rate of a reaction increases. The speed of a reaction increases. All right, good. All right, not much space required for that. Now, the next concept, it's been taught long back, but anyways, we'll learn again. Temperature coefficient. This temperature coefficient is represented as TC. What is this temperature coefficient? Before we define temperature coefficient, let me give you an illustration. Let's understand with an illustration, and then we will see. Now consider a reaction A giving you the product. A is a reactant, P is a product. I tell at 25 degrees Celsius, this reaction to complete, it takes 100 minutes. For the reaction A giving you a product at 25 degrees Celsius, it requires 100 minutes. Now, for the same reaction, the temperature is increased. Temperature is increased. For the same reaction, A giving you product, the temperature is increased to 26 degrees Celsius. Now you tell me what will be the time required for completion of the reaction. Is it 100 minutes, more than 100 minutes, or less than 100 minutes?
So less than 100
Less
minutes.
than 100 minutes. That's also true. Okay, fine. All right. Now for the same reaction, all right, the temperature is raised from 25 to 35 degrees Celsius. When temperature is increased from 25 to 35 degrees Celsius, I tell the time required for completion of the reaction is 50 minutes. The time required for completion of the reaction is 50 minutes. Now just see, at 25 degrees Celsius, the time required for the reaction to complete is 100 minutes. For the same reaction, when you increase the temperature to 35 degrees Celsius, it takes 50 minutes for completion. Can I say from this illustration, when you increase the temperature by 10 degrees Celsius, the rate of the reaction, the speed of the reaction doubles, can I say? When the time decreases by 50 minutes, it means what? The reaction rate increases what? 2 times, or the rate of reaction doubles. So if you understood this, we can define temperature coefficient. Temperature coefficient is defined as ratio of rate constant of a reaction at a particular temperature by rate constant of the same reaction 10 degrees lower to it is called as temperature coefficient. You can see T is a temperature, T plus 10, and here it's only T. So rate constant of a reaction at a particular temperature to rate constant of a reaction 10 degrees lower to it. For otherwise, for an example, we can represent rate constant of a reaction at 35 degrees Celsius divided by rate constant of a reaction at 25 degrees Celsius. We took the example here, 25 and 35, remember. So the temperature coefficient is defined as the ratio of rate constant of a reaction at a particular temperature to rate constant of the same reaction 10 degrees over to it. Now, you clearly explained to me and understood that, not explained, understood this concept. When we increase by 10 degrees, you told the rate of reaction doubles. Now, temperature coefficient, when you increase by 10 degrees, it is 2. Most of the time, gives you the information when you increase the temperature by 10 degrees Celsius, the rate of a reaction doubles. Very rarely, it also increases 3 times. The rate of reaction triples, rarely. So in the exam, if they don't give temperature coefficient, you should assume it to be 2. You should take it as 2. And if they are specific, they will mention it as 2 sometimes, or they can mention it as 3 also. Very rarely for some reactions, very few reactions, on increasing the temperature by 10 degrees, the reaction rate can triple also, all right? But you should consider it to be 2 when it is not mentioned in the question, because majority of the reaction, for majority of the reaction, the temperature coefficient is 2, right? Now, how do you find the rise in the rate using temperature? Rise or increase in the rate? Increase in the rate. Increase in the rate or raise in the rate? Raise in the rate of the reaction. Rate of the reaction. How do you find? We find it by the factor temperature coefficient to the power n. Temperature coefficient for most of the reaction, it is 2. And for very few reactions, it can be 3. If they're not mentioned in the question, it is taken as 2. If they are mentioning, it has to be taken as 3. All right. Now, how do we find temperature coefficient? What's the n? What is n here? N stands for final temperature minus initial temperature divided by 10. Final temperature minus initial temperature divided by 10. That's the value. That's how you find the value for n. Now, for an example, for a reaction A giving you P, if the temperature is increased from 10 degrees Celsius to 50 degrees Celsius, what is the increase in rate? What is the raise in rate or increase in rate? They can ask you, what's the increase in rate for a reaction? How do we find this? In order to find this, now we know that increase in the rate is, increase in the rate is given by the formula temperature coefficient to the power n. Now, in this question, they've not mentioned temperature coefficient, so you should take it as 2. But what is N? How do we find N? N is given by the formula 50 minus 10 divided by 10. So it will be 40 divided by 10. So it will be 4. 40 divided by 10 is 4. So it is 2 to the power 4. 2 to the power 4 is how many times? 16 times. So when you increase the temperature from 10 to 50 degrees, the speed of this reaction increases how many times? 16 times. So we can, this is important to work out some problems in the competitive exam based on temperature coefficient. Is it followed? Did you follow this?
Yes, sir, followed.
Yeah. Few questions we'll solve, and then maybe in the next class, today's Friday, maybe next Tuesday, we'll finish up with this chapter. We'll work some of the questions, and then few more questions to be added on this, and we'll work. Now, people who are absent, you have to watch the videos, the previous classes, and understand. Now, the first question, the increase in concentration of the reactants leads to change in delta H, enthalpy, collision frequency, activation energy, equilibrium constant. It's a very simple, straightforward question. When the concentration of the reactants are increased, the molecules are very close to each other. They can collide frequently. So collision frequency will increase when the concentration of the reactants are increased. Hence, the answer for this question is option B. The next question, the rate constant is given by, the equation K is equal to P into Z into e to the power minus EA by RT. Which factor should register a decrease for the reaction to proceed more rapidly? Which factor should register decrease for energy to proceed more rapidly? Now, if the reaction has to proceed more rapidly, see temperature, collision frequency, energy of activation, and this is orientation. P stands for orientation. We spoke about orientation factor, we spoke about energy factor, and EA is the energy. Now, if the reaction rate has to increase, the reaction has to proceed more rapidly, what has to decrease? What has
Sir?
to...
Sir, is it temperature?
Temperature is in the denominator. What has to decrease? What's in the numerator? Energy of activation. It's a negative value here again. So if energy of activation decreases, it's negative value. EA, the whole factor is negative. So if this energy of activation decreases, if you remember the energy profile diagram also, what I spoke like this I told you energy factor, energy of activation. If this energy, if the peak reduces, what happens? The reaction can proceed faster. So the factor which should register decrease is energy of activation, EA. So the answer for this question is option C. Lower the energy of activation, faster is the reaction. Remember, lower the energy of activation, faster is the reaction. Faster is the reaction. The next question, threshold energy is equal to, what is threshold energy equal to? Direct question. Threshold energy is equal to energy of activation plus normal energy.
Activation energy plus energy of molecules.
Energy of the molecules. It's option C. The next question, for a certain reaction, a large fraction of molecule has energy more than threshold energy. Still, the rate of reaction is very slow. The possible reason for this could be the colliding molecule should be large in size. The colliding molecule must be properly oriented for effective collision. See, this is true. Colliding molecule should not, see, this is, they've written not, sorry, I didn't read this word not. So this happens for you also. It will happen for you also in the exams. So be careful, read the options 2-3 times and then check which is the right answer. The rate of reaction could be independent of energy. One of the reactants should be in excess. So the possible reason could be, for a certain reaction, a large fraction of molecule has an energy more than threshold energy. Still, the rate of reaction is very slow. The possible reason for this could be The answer is option B. I made it somewhere I went wrong in reading. The colliding molecules must not be properly oriented for effective collision. That should be the reason. Even though they possess more energy, that is more than threshold energy, if the orientation is not proper, then it will not be an effective collision. Therefore, the answer for this collision is option B. Option B. The concept of energy of activation. I taught you about energy of activation, all that transition state theory. Transition state theory we do not have in our syllabus. We will, but anyways, we will learn the transition state theory and the other factors in the next class. So this is the reaction. This is the energy profile diagram which I was talking about. This is potential energy which I was talking about. This is a reactant and products. I took a specific example, H2 and I2. Here they've given a general representation. All right, transition theory and the other set of questions we will do it in the next class. All right, and wind up with chemical kinetics. All right, any clarifications?
No, sir.
All right, sir.
Yes, sir. Yeah. Thank you. Thank you, everyone.
So can I stop the class?
Yes, sir. Yes. Yes.
Thank you, sir.
Yeah, bye.
Bye, sir.